All right, we're back. We are Game 2005 in the fall 2018 semester at George Brown, and we are week 8 officially, but lesson 7, part 1 of our broadcast. We're talking about circular motion today. Again, as just I mentioned earlier, for the people that were in the class, sitting at week 8, we have 2 weeks until your assignment 2 is due, right? Which I want to talk about today in a lab and this week in lab in more detail. Some people have funny questions, and I want to work with you guys in doing that. Give you some time to do that kind of stuff this week, and then week 11. So we're 3 weeks away from our test number 2, and again, I will be providing a cheat sheet that you can build upon. That's coming up. I know I'm like a broken record. Sometimes I keep repeating myself, but people forget. People ask me questions on the day of. So do we have a test today? I don't know why they would ask that question, but you know, people don't come to class and they have their own reason for being. Anyway, so that's kind of announcements. SDL. I'm probably going to put up by the end of the week another version of the SDL template. I was hoping to do it the week I left, but I haven't had a chance to do that yet. And I'm still in the process of marking assignment 1, which is holy cow. Lots of variation in terms of what I saw. Really good assignments and some really poor assignments. Like, let's just hand something in. Let's just hand anything in. Let's just hand a blank piece of paper in. Seriously, right? So yeah, so it's like really bad and some really good stuff. Like I've noticed some really good stuff. I saw some awesome assignments, you know, that were handed in. I would say probably the closest to perfect I've seen in a long time. You know, so they're going to get really good marks. But yeah, I'm in the process of doing that, so please bear with me. For the most part, everyone did well. Like the groups did well enough that you guys are going to be delightfully surprised in terms of the mark. I'm not a hard marker when it comes to this stuff, so you know, just bear with me. So today we're talking about circular motion. We're talking about extending Newton's laws, and it does. The last lesson that we did talk about a little bit of circular motion. Centripetal force, all that kind of stuff, if you remember from the last time, right? I know it's been a couple weeks now, so it's out of your brains, and I'm just going to review that part. So think about these, you know, objects traveling in circular paths. Like if physics was only linear, okay, that's cool and all, but pretty boring. And especially in your video games, you want some kind of circular motion, but we have to think about this circular motion in terms of how it would work in physics. Now, I'm trying to think of a game that would really be good like that. Can anyone think of a game that you have a lot of circular motion, physics circular motion, not just something that goes around and around, all right? Okay. Okay, anyone else? There's not a lot, right? How many games do you know that you have like real circular motion? Like, you know, where you have some kind of thing that works with physics. However, you could make a, you know, some kind of car, more realistic car, where you have some kind of the wheels actually turn and have some kind of friction and all that kind of stuff, acceleration. You could do that if you want it to be almost like a car simulation. And I think some of the circular motion here would apply, as well as when you whip around car games, when you whip around the bend, how your car would stay on the track and so on. That has a lot to do with what we're going to be talking about this week. One of the things it talks about here is objects moving through a viscous medium. Okay, what the heck does that mean? So viscosity is almost like, if you think about like thickness or the ability for you to, if it's more viscous, I always think about like, you know, the blood of the chthon being viscous as it pulses out of the chthon's neck, right? I don't know. Don't get me wrong, it's 8 o'clock in the morning on a Tuesday, so I have these funny thoughts in my head. But viscosity means like this thick fluid, usually. That's when I think about viscosity. The thicker it is, the more viscous it is. It's not as liquidy, if you will, right? More you know, more like syrup, or more like, you know, something like a I don't know, something that's thicker. Well, viscous medium, what does that mean? But we are living in a viscous medium, right? If you think about this, our air is that there's a bit of viscosity in our air as well. You know, and you can really feel it in the dankness of the deep in the city, deep in the dregs of the city, where we have viscous air, right? Okay, no, we don't. But you know, I can only imagine this, you know, some kind of cyberpunk 2077 kind of, you know, situation where we have a lot of air that's pretty dank and viscous. But typically, yeah, so a medium could be anything. It could be the air, it could be water, it could be, you know, some kind of stuff. And what happens is motion, as some kind of particle travels through a different kind of medium, usually it slows down. That's what happens. It gets affected by you know, almost like the container that it lives inside. Think about our Earth as a big container with some kind of fluid, the air. Our air, the fluid that is our air is pretty not so viscous. Otherwise, we wouldn't be able to swim in it, right? But we do live in mostly invisible, you know, atmosphere. We can't normally see it, and we don't normally feel it. We're just used to it, right? Maybe for an alien, they look at us, they're like, hey, those human beings, they're swimming in some weird viscous fluid, right? But for us, I use viscous a lot today. All right, let's move on. So uniform circular motion, we talked about last time, where you have centripetal acceleration is equal to v squared over r. All right, so that is the formula that you're going to need to understand the centripetal acceleration. Who remembers where does the centripetal acceleration point to? Does anyone remember that? Doesn't say it on the slide. So where is the circular acceleration? So the centripetal force, where is it going towards? Anyone remember? This is part of your, yes. Yes, it's correct, the center of the circle. So you have some kind of circle, the center of the circle, and as it's whipping around the center, you know, the acceleration is going toward the center of the circle. That's centripetal force, right? And then again, the centripetal acceleration, where it looks like there's a acceleration vector with a little c on the bottom, is equal to the velocity squared over r. And it says that the centripetal acceleration is always perpendicular to the velocity. All right, so if the velocity is tangent to the wheel, let's say, or tangent to the circle, if you think about this, right? And then it's perpendicular, means it's going at a right angle. Perpendicular means right angle to, and that's how it works. So again, there's no change in speed, only a change in direction. And you can see here that we have some kind of particle that whips around this area here, and you've got the force that's going towards the center. The sum of all forces is equal to mass times the centripetal acceleration, which is equal to mass, right, times v squared over r. So you can re-simplify our formula for the sum of all forces going towards the center of the circle. All right, does that make sense? Again, just a little bit of review, right? So what we talked about last time, because we just kind of touched on it, but then, you know, we have something like this. And it says this is a puck that kind of goes around in this circular path. So kind of simple stuff. All right, so again, if the string breaks, where is the puck going to go? Is that me?
Yep.
Gosh darn. These people. Discord. So, yeah, you know, it is what it is, right? Just nonstop. Let's just ping Tom. All right, yeah. So it gets whips around here, and then what happens is if the string breaks, where is it going to go? It's going to fly off of this. Think about this as a rail. All right. So while the string is here, this puck is on rails. It's going to keep going like around and around the circle in the same way. But if the string breaks, the puck is going to fly off again, perpendicular to the centripetal acceleration, right, which is in this direction, right? So it's going to keep going along the velocity vector that it was on before the string broke, right, which is usually tangent to the circle, whatever that is, right? So it's going to go whoop, whip away. And if you think about what this is, think about, you know, a car going around a ramp, like we talked about before. So the car is going around a ramp, the circular part of the ramp. And then what ends up happening is, imagine if somehow the string doesn't break, but the friction, the force of friction along the ground, around where the weakest part is, as it's whipping around the corner here, let's say it's an icy road or something, it's almost like the string breaks and the car goes into the ditch, right? So that's how it goes, because you have this force and then it goes right into the ditch. So that's usually how it goes, straight line path, tangent to the circle. All right, so again, you can see that in this particular case, you've got a situation that you might get a question like this, where you have, okay, so some kind of string attached to a rope to the ceiling, classic example again, where you have something that goes around in a circle, right? And if you notice, if we drew the free body diagram for this in this particular case, we would draw it like this. mg, right? So the force of gravity times mass, that's the first part. That's this part of the free body diagram. And then we have the force of tension, right, coming along this string that connects to the ceiling, right? If you think about that. And then, so that's one of the things. We have a radius r, that's what we have. And you can see that there is some kind of angle theta, right, that this string is kind of angled at. It's not perfectly straight. If it was perfectly straight, there wouldn't be any circular motion. It's away, and it's traveling in a circular path, right? So if you notice, if we break it down into two components, we have the sum of all forces across the y-axis, right? The y-axis that's up and down must be 0 because guess what? The thing is not falling down, right? So that's good. And that equals, if you think about the tension across the, cos theta, remember when we talked about this? It's interesting when we look at this particular situation, typically what we say is that cos is along the x-axis and sine is along the y-axis, associated with the y-axis. But in this case, it's reversed, okay? And it's because of this centripetal motion, this circular motion. So we can say that T cos theta then, whatever that is equal to mass times gravity, right? That's what this means. So that's where the sum of all forces is equal to 0 across this thing, almost like the normal force, if you think about it, right? So there's something that's holding up this particle, and it's the tension on the wire, if you will, especially across the y-axis. The component of the tension on the y-axis is strong enough to resist the force of gravity, so it doesn't, so that the particle doesn't fall to the ground or spin off into oblivion, right? Into the viscous fluid that is just trying to use that word again. All right, so then we have the sum of all forces across the x-axis this time, this way, right, is T sine theta, which is equal to, if you think about it, mass times centripetal acceleration, which is the one that goes towards the center of the circle, right? So if you know that this equation is true, then this is good. I mean, this is where you can, once we have this kind of relationship, we can figure some stuff out, all right? We can kind of, as long as we know some unknowns, we can get the other portions of our formula. So again, it says V, which is velocity, is independent of mass. Doesn't matter, right? Because mass is being supported by, by the y component. The y component is being canceled out. There is no up and down motion. It's just circular motion around and around on the horizontal plane, if you will, right? And so we can say that you can figure out V as the square root of the length of this particular rope or chain or whatever kind of connection you have here, times gravity, times sine theta, tan theta. Okay, so this is kind of an identity, if you will, when we look at centripetal motion or for a conical pendulum, which is the condition, the scenario that we're talking about. Okay, so what I'm describing here is one classic example that you might see on a test. Okay. Please stop me if you have a question. So again, we have this different kinds of motion. So one of the motions that are circular is motion in a horizontal circle. So it's going around and around horizontally. All right. And we know that when we're going around horizontally, the y component in a perfect horizontal circle, so it's not wobbling, okay? It's not doing one of these. It's not my hand putting it around. It's some kind of motor or some kind of other thing that's doing it, right? And let's suppose that the particle is perfectly shaped and that there's no air resistance, okay? So something that's going to make this run around very nicely in a horizontal arc, if you will, right? Then we know that velocity then can be the square root of, okay, if you think about this, tension times radius over mass, right? So the force of tension times radius over mass. So that's the tension of the cord, chain, connection, whatever you want to call it, okay? All right, here's the next scenario. I have a, this horizontal flat curve, and my car, the model car, we can think about it as a particle that's traveling in a uniform circular motion around, this bend, if you will, or a bank. And we can see the model car as a particle in equilibrium in the vertical direction. So that means that it's not going to fly up into the air or sink into the ground, right? The car is stable on the road. The normal force, if you will, is pushing the car up from the ground, right? And yet we have this motion, and the car is able to stay on the ground. The wheels are able to, because they're made of rubber. Remember the whole force of friction, static force of friction and kinetic force of friction, right? What's the difference? Static friction and kinetic friction? Anyone remember? Come on, who's gonna? Oh yeah, go tell me.
Static is much higher, so it takes a larger force in order to get the object to start moving. And as soon as it starts moving, the kinetic friction is smaller. The
stuff that's trying to stop it from moving, right? Yeah. So that's good. So static friction, just like Nick said, is think about it, something that's going to try and stop you from moving, right? Remember, an object at rest tends to stay at rest. Newton's one of Newton's laws, right? In fact, that's the first law of motion, right? An object in motion tends to stay in motion, right? So that's the thing. So think about this, where you have an object at rest, even if the car, there is, if I have wheels, this is where the wheel was invented, right? Think about this, right? If the wheels on a car weren't wheels, and if they were, I don't know, squares or something weird like cubes, right? The car would be very hard to move, right? And it would kind of bounce around, and it would have some weird action happening or whatever, right? So the wheel was invented because, it was a natural thing, figured out that, hey, if something's curved, then it's going to roll. But the thing is, even for a wheel to get moving, you need to, what are you using? How does a wheel move in the first place, right? The wheel's rubber connects with the cement, right? Let's think about molecules for a second, just for 1 second. I'm not a chemistry guy, but let's just think about this, right? You have the molecules that are interacting between the rubber and the cement, right? That's what ends up happening. And those molecules that interact, right, this is the friction that it causes to this kind of friction. Friction equates to heat, if you will, right? Some kind of lost energy, right? Think about the energy of a system. I'm putting energy forward, but some energy is being lost, right, because of the friction and the wheel, and also how smooth the axle is in terms of motion. Usually cars are very smooth these days. It's not like they're a rusted axle that you have to move forward. It's like our modern cars are very beautiful, and they'll move. If you just take the parking brake off a manual car, it'll just roll down the hill, right, on its own. So, there's very little friction there, very little resistance, if you will. So you've got that, and you've got a little bit of loss. But the way the car moves forward is it uses the friction of the wheels, the rubber on cement, to push itself forward. Basically what it's actually doing, if you think about it, is I'm doing one of these. I'm pushing back right along the ground. So I'm grabbing the ground, and then I'm pushing it. I'm pulling against the ground to pull myself forward. That's what that car is doing. Think about it, right? As the wheels come down, grabbing the ground, pulling the car forward. That's what it does. But what about around a bank? How does that work? So I'm going around a bank, and do the wheels travel at the same rate of speed? This is beyond the scope of the course, but think about this, right? Are both wheels spinning at the same rate, right? And if they are, because you got a wheel that's on the inner side and the wheel that's on the outer side, these are all considerations that you do from a simulation perspective. But we don't care about that kind of stuff. All we care about is that when we simulate a car, that the force of friction, the force of static friction going this way is the stuff that is supporting the car, right, from spinning off into oblivion, not the force of kinetic friction, right? Why static friction? Because the wheels are this way, right? They're perpendicular to the curve, right? So again, if you think about a car, if my wheels are with the road, I'm going this way. There's no friction this way except for the friction on the road as I'm grabbing and moving across the road. But what about this way, right? The car to slide or to shift, something like that, right? To drift, if you play one of those kind of car games. Who drifts in the car game, right? I drift a lot in the car game. But anyways, so if you have this drift happening, right, there is a force of static friction across the perpendicular of the wheel to stop the wheels from moving, right? And that's what's keeping the car straight on the road, right? So again, you got the normal force that pushes the car up, and mass times gravity pulling the car down. These vertical, the car's said to be in equilibrium in the vertical direction. But across the horizontal direction, right, we have a relationship with where velocity is equal to the square root of the force of, or where it says mu. Mu is the coefficient of static friction times gravity, and then times the radius of the curve. So there is this relationship. Okay, again, these are all kinds of formulas that you'll have access to, of course, on your test, right? So it's nothing that you. So if again, what's the velocity if I go around the curve? Well, it really depends on the radius. So if the radius is larger, right? A larger radius means that this curve isn't as it's not so extreme. The larger radius means that the curve will be more flat, right? Because think about the radius on the inside. When I draw the circle, it's going to be flatter and flatter. If it's a smaller radius, that means the curve is going to be greater, a crazy radius, right? And that means that, you know, if this is a smaller number, then velocity is going to be a smaller number. There's a relationship, right? And it's almost, there's a proportionality between the bigger, the larger the curve, the more speed I can go across around the bend, right? The smaller the curve, the less speed I can go around the bend, right? And then there's this gravity thing, right? This gravity thing that makes a difference as well. I mean, you might say, well, that's going to be a constant, so why do we even have to calculate it? Well, you want to get the more accurate velocity. But we usually use this in terms of when we're whipping around this horizontal path, you know, for other objects, like it's not a car, it's something else that's on a horizontal. For example, a rocket ship that's tied to a, some kind of particle beam that's keeping it, stable, with the, I don't know, I'm making this up, with the space station that it's whipping around. I don't know. And this can be used for the same thing. Now, except for that the, in this case, I'm not sure that the coefficient of static friction would make any difference, right? But that's how, this is the relationship that we're talking about here, okay? All right, so we got this bank curve, right? So one is a flat curve, the other one is a bank curve. And usually the reason why we have a bank curve is we want to help the car not fall off the rails, if you will, okay? So think about the curve, as you're moving, you're turning onto the highway, right? This bank. Normally it's not like this, not flat, right? It's like this. It's kind of curved towards the center of the radius of the circle, right? And the reason why, if it was like this, that'd be okay normally for, if it was completely flat, maybe in the summertime it'd be cool. But what about rain? And what about snow? What about ice? So it's safer to do this, right? Kind of put it on an angle towards the circle here, right? And when we do that, then what ends up happening is you have an additional help from the bank to help the car stay in line and not fly off into oblivion. Okay. So again, so model of the car as a particle in equilibrium in the vertical direction again. So we have this situation, right? And we see that the angle of the bank is found by the tan theta v squared over r. This v squared over r, if you think about what that is, right, reminds me of centripetal acceleration again, right? And we've got our g, so v squared over rg. So I want to find the angle of the bank. There's a relationship between the velocity over the radius, and this is the proper angle to keep this car on the road, right? And again, notice that there isn't any mention at all of the force of static friction in this formula, although in the free body diagram it is mentioned, force of static friction, right? So, all right, so let's continue. So again, the angle independent of the mass of the vehicle, it doesn't matter, right? And if the car rounds the curve at less than the design speed, the friction is okay, right? But if it goes more than the design speed, so the angle is like it goes way faster than it should, then it's going to potentially, again, fly off into oblivion, right? So when you see those signs in the road, guys, and it says 60 kilometers, right? As you approach, or 40 kilometers, or as you approach the bank, there's a reason for that. Because that bank, that road, the ramp that goes on, the off-ramp or on-ramp is designed for something along that speed. Is it designed for 40, by the way? Does anyone think? If it says 40, is it designed for 40? Nah, it's probably designed for a little higher, not much, right? So don't try to do 100, right? Or something crazy like that. You might, depending on the handling of your vehicle and the size of your vehicle, if you're driving like an SUV or something crazy, and if it's you kind of whip around a thing at 100, depending on your handling, how good you are at the car, it may, and compensating for the bend, you might fly off into oblivion, whether it's off a bank or just, you know, tip over, right? So, but usually it's 3 times from what I understand. Usually they say 40, it can probably take 120 max if you're really good at as a driver. But I don't believe that. I don't think it's that high at all, right? Especially some of the roads, especially like on the 400 and 401, we got stuff that tips over there all the time, right? So they have the rumble strips. Rumble strips add additional friction to the road, right? And also tell the driver that it's supposed to, hey, driver, you got to slow down here because we've made this road. This bank is very, very horizontal. There's not a lot of bank on this road, which means that if you whip around this thing, you're going to go into a pole or something like that. We haven't been able to. Sometimes the engineers can't design a bank with much of a curve because of the way that the ramps all kind of convolute together, right? So just, you know, just be careful. Anyways. Okay, now this is one of the questions, or one of the situations that deal with one of the questions in your assignment. I think it's the last question, R2D2, right? The one that goes around. So what we have is in the Ferris wheel example, now we have a different kind of motion, circular motion. The first type, horizontal type, right? We only have the force of gravity going down all the time, right? And usually, especially if it's tied to like some kind of conical motion on the top, where we have something tied to the top, or if I'm whipping it from the side, there's not a lot of vertical flow. Like we don't have any kind of motion like this too much, right? And maybe in a real world example, if I'm whipping it over my head mechanically with my arm, I may not be as accurate, you know, as a machine, let's say, right? But here we have a different situation. We have vertical motion, right? And what happens is this vertical circular motion, it's not consistent, if you will. Even though there's uniform circular motion, we have different forces acting on the particle at different points. All right, and this is the exercise that I've given you for your assignment. All right, so think about this, right? I've got velocity, all right, and I've got velocity going up, and then I've got velocity going to the side, and I've got velocity going down. But at the same time, you've got gravity, right? And I talked about this in class, right? Where you have gravity going down, velocity going down, right? You have gravity going down, velocity going to the side, to the left. You have velocity going up and gravity going down, right? So you can see that potentially at this point in space, or maybe this point in space, you might have the most forces going, because the forces are pointing in the same direction, right? They're pointing down, and we'll talk about this in a second. So think about the child. If there's a child that's inside of the car of the Ferris wheel, and think about the gravitational forces at the top and the bottom. So where is the gravity, where does he feel the least heavy? And where does he feel the most heavy? Think about that. So I've got vertical motion going this way. It looks like it's coming up this way, right? And at the top, is he feeling lighter or heavier? Compared to other places on the wheel. So think about what he feels like.
Going up, because that's when he's moving up the fastest.
So here he's moving up, right?
That's when he's moving up the fastest.
But the ground is pulling down, so we've got upward motion and downward motion, right?
Him against the seat, that's the highest normal force of the seat up again.
Okay, all right. What about down here? What's happening down here? So I'm just putting it up to, you know, kind of thinking about this, right? So you've got, you know, you've got, okay, but think about this. What about over here? So I've got forces going down, and so velocity going down and gravity going down. So would it be heavier here, here, here? Where would you feel heaviest, right? Yeah, so I want you to think about this, because it's one of some of the questions that when you draw your free body diagram at different points, you can understand the forces that are playing on the Ferris wheel. Now, this is a really great example, guys, for your games as well. Not because of circular motion, but I want you to think about the sum of all forces. So you can use some of this example like, okay, what if I had wind force? What if I had a bunch of different forces from different directions in 3 dimensions? You know, how would I use them to, you know, manipulate the direction of my of a free body in space? Like, how do I do that? So this thinking that we're talking about, where you make the free body diagram, even though our free body diagrams right now are in 2D, right? We're still talking about 2D motion, if you think about it, right? You can apply them to 3D, right? This free body diagram, right? We don't have anything on the Z direction right now. There's nothing going in and out. Like it's not like the Ferris wheel is on some other kind of arm that goes like this, ooh, kind of in and out of the, in and out of space. That would be a really weird motion, by the way. If you're going like this and then plus doing one of these, I mean, I think there's some rides like that, but it's kind of weird, right? So, but you could apply free body diagram to this kind of stuff. So think about this part. The child is the particle, okay? And if you think about it, right, at different points in space, right, you can see that if he's at the bottom, right, if he's at the bottom, there is the normal force on the bottom, if you think about this, is happening, right, at the bottom. And the normal force at the top is also the same, right? Bottom and the top, up and down, right? You have an upward force and a downward force, right? So from that perspective, right, we can say that the sum of all forces at the bottom, right, as an example, minus mass times gravity is equal to mv squared over r, right? Where we say that the normal force in the bottom, if we want to find the normal force in the bottom, is equal to mg, and when we simplify, times 1 plus v squared over rg. So this is a great formula to use if you want to find the normal force at the bottom of the Ferris wheel, okay? How do we figure that out? Again, normal force at the bottom, right, minus mass times gravity, right, is equal to mv squared over r. This is the mass times the centripetal acceleration towards the middle. That's what v squared over r is, right? And that's how we got this formula. But what about the top? Notice that there's a difference, right? So one subtracts mass times gravity, and the other one adds mass times gravity, where now the normal force at the top is different. It's mass times gravity v squared over rg minus 1. Why is that? So normal force at the top then would be greater, would be lesser. Think about the formulas that we got. Take a look at these two formulas. So is this normal force at the bottom? It's 1 plus v squared over rg, right? So let's take this 1 away for a second, right? And then, because then you're going to have mass times gravity plus mass times gravity, v squared over rg. We can take the gravity out, the second part, where we have mv squared over r, right? That's what that works out to be, right? If you multiply it through, right? So yes.
Why is normal force different from gravity at the top and the bottom? Because it's not moving up or down when it's at the top or the bottom.
Well, this is the thing. Where is the centripetal acceleration going? Right? That's the thing. That's the thing that we have to think about, because we have a force of tension that's pulling us or trying to rip us away from the center of the circle, right?
At that moment, you're balanced, right?
You're balanced at the top and you're balanced at the bottom, but there's still a force of tension that's going towards the center of the circle, right? And so because of that, think about this, right? At the bottom, right, then you have this, you're subtracting mass times gravity, because what's happening is you're going further down, right? Whereas on the top, right, you're adding. So where, again, think about this, where's the normal force less? The top, right? That means if the normal force is less, the child feels lighter at the top than he does at the bottom due to the centripetal acceleration, right? That's what's happening. I'm just putting this out there because you know what? You can feel this if you've ever done a roller coaster. Centripetal, by the way, the Ferris wheel and roller coaster examples at different parts of the roller coaster, you still have that same centripetal acceleration that you're feeling because of the curve, right? The roller coaster is not straight. If you're at the top of the roller coaster and you swing down on the bottom of the curve, right? You're feeling this centripetal acceleration that's pushing up because it's a curve, right? And the same thing at the top. At the top, right? You're being pushed back by gravity, sure, because you're in your seat. You're not any heavier or whatever, but at the top of the roller coaster, you feel, especially if it's going up. You ever be in a roller coaster and you feel like you're going to fly out of your seat? It's like you're coming out off your seat. And that's what the child would be feeling as well. He's going to feel like he's lighter at the top. He's going to fly off. Whereas at the bottom, especially when you come down a roller coaster really quickly, you feel a lot heavier at the bottom of the roller coaster. Like you feel like gravity's pressing down on you, right? It's not really true. But think about that from a fighter pilot. Think about circular motion when you're flying a jet plane or something like that, right? So I've got the force of gravity, and as I'm climbing, I have the force of gravity on me, right? But as I'm going down, as an example, I'm going in the same direction as gravity, and I'm picking up speed, so I feel heavier on the way down. So imagine right at the bottom of the curve as I'm banking back up with my fighter plane, how much gravity, the force of gravity seems a lot heavier as I'm banking up from a descent. Okay, I'm trying to make it so it's, we can talk about it. All right, so again, they give some other examples here. Think about a ball in a circular path, right? And because of the gravity, the speed of the ball is not uniform, right? You've got some, now Ferris wheel is mechanical. That's why this example is here, right? Ferris wheel is mechanical. You're on an arm, right? You're being held by an arm. You're not being held by like a wire or a cable, right? A ball is a different situation, right? Where you're whipping around and it's not a mechanical motion the same as a Ferris wheel, right? So the force of gravity, right, on the speed of the ball is not uniform because of the direction the ball is going, right? So a good example is the centripetal force, and again, it's hard to see this little diagram. Let's bring it a little closer so you guys can see this. So we've got this, V min, right, as an example, is at the top, and as your velocity is going down this way, it accelerates to come to the bottom, and then you've got your maximum velocity as you come down, right? So it's almost like it's accelerating and decelerating. So it decelerates as it comes up, and then as it comes down, it accelerates as it comes to the bottom, right? So because it makes sense, right? I'm going to, if I've got a ball, I'm doing this on the downstroke of the ball, right? Of my cable, it's going to feel a lot faster than on the upstroke, right? Okay, again, we're just talking about some things we can notice in the real world, right? How does this apply to your game? You can do that. You can make it apply to your game. But again, I haven't seen a lot of games that use that kind of mechanic, if you will. That, you have a game that's on rails, or you're on a roller coaster that, makes you fly off. Maybe there's some games you noticed like that, but I don't know there's a lot of games like that. Okay, but usually what we use is we use circular motion for things like jet planes and that kind of thing, right? So, or other paths, right? All right, so again, I've broken it down like this. You've got at the top and at the bottom what the situation is. So again, if you want to find the tension of the cable at the top, what's the tension of the cable at the top? It's mv squared over r minus mg, right? So again, the formula has just been reworked, moved around a little bit. And the tension of the cable at the bottom is mv squared over r plus mg, right? So why? Because the force of gravity at the top is working against you, right? Whereas the force of gravity at the bottom is working with you, if you will, right? It's in the same direction as your velocity, right? So switching around the signs and everything else, it works out to be a different kind of formula. By the way, this is one of the things that's going to help you develop a general formula for motion around a Ferris wheel, which is one of the questions I asked you with R2-D2, right? So think about how to put together this formula at the top and at the bottom. So we got this idea of non-uniform circular motion, right? So again, the acceleration and force have these tangential, God, that's a terrible word, tangential components. Say that fast, tangential acceleration. You've got the, so basically this force, and if you notice like where the forces are, you've got this force T, right? As an example, this is the tangential force, right? And you've got the force across the radius of the circle, right? Here's the circle where you have the sum of all forces. You can see the sum of all forces. We're not talking about velocity or acceleration now. We're talking about Newton forces, right? So forces in newtons pushing in a particular direction. So you can see that as the ball travels around the circle, in this particular case, you can see that the force is going to be an angle, to his velocity the force tangential, and the force radial. Okay. So just wanted to, to kind of, to kind of show this relationship. And if you think about this, right, the radial force is, produces this centripetal acceleration because force is equal to ma, right? So mass times acceleration. You can kind of, if you know what the acceleration is, the centripetal acceleration, which is v squared over r, then you can relate, mass times v squared over r, which is the force, towards this radius, right? Okay.
Question.
Yes.
The last slide, it showed us all the formulas for that motion. So in our assignment, what we have to do is just replace those things, or do you want formulas based on like the angle it forms?
Yeah, I'll talk about that in a bit. I'm gonna go over the that stuff when we hit lab this week. I'm gonna talk about that. Actually, then I can spend more time with it. But yeah, it's basically I've given you what you need. You just have to rework it, right? But I want you. Remember the assignments are not just there to trick. They're not there to trick you. They're there to make you think, right? Because you're going to have to solve your own problems from a physics perspective when you make your games, right? That's what it's about. So the assignments are not there to be like, okay, it's not just preparation for the test. It's also, hey, what can I learn from doing this assignment? That's what the thing is supposed to be, right? And they're not supposed to be hard. Not supposed to be hard. It's like you work with your partners. You talk about physics with your partners. That's what it's about. And then you get your assignment done, right? And it gives you a chance to do that. The stuff where you can really practice, though, is the lab, little lab exercises that I'm giving you. Please practice those, right? Because if you practice those, you can do better on the test. All right, so here's vertical circle with non-uniform speed. So here's where we have, again, the gravitational force, is pulling down here. So think about this, right? Why does it look the way it looks? Okay, so we've got this tension at the top, right? And we have tension at the bottom, okay? And the tension at the bottom, notice the tension at the top it seems to be less, right? The actual vector seems smaller. The magnitude of the vector of the tension of the top of the string seems to be less than the tension on the bottom. And that's counterintuitive. You'd think that the top of the circle is where the thing would fly up the highest, but actually it's at the bottom of the circle because the bottom of the circle has a lot more tension because mass and gravity and your velocity are all going in the same direction at the bottom, right? So, or close to the bottom anyway. So think about that. When you draw these two free body diagrams, the velocity at the top, you've got a velocity vector this way, you've got tension at the top going this way, and mass times gravity going toward the center. And then when you're at the bottom, notice that the tension at the top, it goes in the opposite direction. These go in the same direction, right? So again, these are just observations of how this thing works. So you can say that the tension at any point can be found with this general equation, right? So going to what Ricardo said, think about this. The tension at any point can be found with this equation. V squared over RG plus cos theta, whatever that angle of is that you're expressing, right? That makes sense. So you can find the tension across the cable. This is a key formula that you're going to need, right? When you're asked a question like, what's the tension of the cable at this particular angle at this particular point in time, right? And there's the tension at the bottom. And notice that it says the tension at the bottom is a maximum and the tension at the top is a minimum. And the reason why that is because of the centripetal acceleration, right, works with gravity to pull things down towards the center at the top, right? Whereas the gravity, when it's at the bottom, is pulling down, and tension at the table is pointing up, and you've got the velocity also coming down. So there's a lot more tension of the cable at the bottom than there is at the top. Okay, so going back to that child example, where does the child feel heaviest? At the bottom, right? Typically. So if that's true, if tension at the top somehow is minimum, and let's suppose that the tension at the top is 0, right? Let's suppose that, then we can say that the velocity at the top is equal to the square root of gravity times radius. Okay, so that's the some additional formulas for you. Okay. Now this talks about frame of references. Remember we talked about frame of reference. I said that frame of reference, the whole notion of frame of reference for this particular course is not really relevant. It's relevant if you're a physicist, all right? We're not physicists, we're gamers, right? So I can talk about, you know, accelerated frames of references all I want, but it doesn't make any sense for you in your game. So we're gonna skip this slide. It's there for completeness, but it's not there for, I'm not gonna test you on it on a test. I'm not gonna ask you these kind of questions. I just want you to think about what this means, right? So this idea of a fictitious force, right? We don't really have a real force, right? It seems like we have a force. And this is where we have this idea of how does a child feel, right? But there isn't really a force. It's just, you know, it's depending on his, his notion, right? So here we talk about this idea of centrifugal force. So think about being, you know, someone being in a centrifuge. You ever see those rides? There's these rides at Wonderland, right? Where you sit on this. You ever try those rides? It's a terrible ride. Okay, you actually stand up in the ride, right? And you're at the, you know, the edge of the cylinder, right? That's what it looks like. And the cylinder just spins around, right? And you feel like you're going to just like toss your cookies a couple times, right? When it's doing this. And this is just when it's in the horizontal. Then it does kind of the vertical. It kind of hangs you out. Does the other way, right? Goes this way. Does all these weird things. And you're still stuck on the edge of the, you know, of this thing, and you feel like you're going to fall into space, and you feel afraid and all this kind of stuff. I would feel afraid too. And who knows what it's doing to your insides? I always think about that, right? You're in a centrifuge, man. What the hell is what the hell is it doing to your organs and your blood, right? And your brain, right? I always think about that stuff. Let's just spin a human being, you know, like inside of a centrifuge and see what happens, right? So I don't go into those kind of things, and I mean, that's just my perspective. Maybe I have you know, a fear of like flying into space or something, I don't know. But, or something breaking, imagine that. So you're in a centrifuge and it breaks, right? Woohoo! Yeah, and that's just not something I want to do. So, but the thing with the centrifuge, the way it works is you have this fictitious force. This is the idea, where the fictitious force, you feel like you're being drawn into the center of the circle, right? Well, think about that as imagine if how you're feeling as a passenger of a car, right? So you have the car has is, you know, you've got this, you know, the wheels on the ground. The wheels have this force of static friction that's holding it on the road. Depending on the bank that you're on, where does the passenger think he's going to go? How does the passenger feel? Passenger, especially if you're in a seatbelt, that's why we have seatbelts. If you didn't have a seatbelt, where would you feel like you're going to go? As a passenger in the car, think about yourself in the passenger car. You're turning the road. You're turning on the left bank. Where are you going to feel like you're supposed to go? Like where you feel your body's going? Outside of the car. You're going to fly out, right? Yeah, I had a very bad example when I was a kid. I was like a kid, and we had an old car. That's why I don't buy old cars anymore. And back then, the actual, you know, the doors could actually open when the car was moving. Like there wasn't like automatic locks on the door. I don't know if you guys anyone had that kind of car? Like, yeah. So you have no automatic locks, and then somehow the door is open. It opens up on the highway, right? As I'm bounding around a curve, right? And I find myself in space. I'm not joking around. I had one hand on the door, and one hand on the seat, and I saw road, right? It was pretty good as a kid, right? Yeah, back in the day. Anyway, so yeah, so you tend to feel this fictitious force that wants to send you flying outside of the car, and that's why we have seatbelts, right? We have seatbelts because if you don't, this idea of a fictitious force, you're actually feeling, you know, forces that are on you because you're inside. The centripetal acceleration is this association with the car's change in direction is giving you this centrifugal force, right? Again, do we really care about this stuff in for us? Well, again, you know what it says? It says it's basically related to Newton's first law, right? Why? Because an object in motion tends to stay in motion in the same vector, right? I want to go this way. You push me this way. I want to keep going that way. Wait, you're turning me? No. I'm going to provide some tension now. I want to go this way because this is the way I was going. Wait, you're turning. You're adding energy to go this way now. Whoa. That's what's happening. And so it gives you this feeling that you're going to fly off. Okay. Again, am I going to talk about Coriolis force or anything like that. It's neat stuff, guys. It's really neat stuff. And if you want to read about it, there's some great articles on the internet, also in your physics books about the difference between apparent forces and fictional forces and real forces and all this stuff around a curved path. But in our games, for the most part, unless you're doing some kind of weird artificial intelligent motion with, you know, flocking and I don't know, something else that you want to use, I don't know, some kind of circular effect, you know, to do some kind of simulation, you're not going to need to know any of this in a game. All right. Just going to keep going. So here's some fictitious forces in linear systems. I'm just mentioning this again. Am I going to give you a question like this on a test? Hell no, right? I'm not going to do that. But I want you to think about this. If there's something in this particular case, this person has a different frame of reference. So the observer has a different frame of reference than the person that's in the car, right? If I'm in a car, right, my frame of reference is, does it feel like I'm actually traveling really fast when I'm on the highway in the car? No, like my body's not physically. Okay, and again, I liken this to local and global coordinate spaces, right? So think about this. My body is parented to the car. My body is the child object of the car game object, let's just say, right? So inside the car, I don't feel any forces typically, right? Unless I kind of make a curve. If I turn off really a bank or slow down or speed up, that's when I start feeling the forces of the car, right? For the most part, or if I crash, that's the other thing, right? If I crash, if you collide with something else, you have a collision, then you feel something, right? But typically you don't feel anything in a car. You feel like your body's in equilibrium, but actually your body's traveling really, really quickly, like, you know, 100 kilometers an hour on average on the highway, right? So yeah, so then there's a different frame of reference. And again, I'm not going to talk about it too much, but I want to just mention it because, you know, we're talking about physics. It'd be remiss if I didn't mention these kind of things. And that's really it. We're talking about examples. So again, this week we're going to work on when we're in lab, I'm going to get you to work on your assignments, right, early, because there's some other stuff I want to introduce next week, and you're not going to have time to do that next week for your assignment. So we're going to do it this week, okay? All right, so here's a more complete conical pendulum example. So I put these in here in the book, from the book, because I want you to see the exact example. So here's an example. A small ball of mass m is suspended from a string of length L. The ball revolves the constant speed v in the horizontal circle of radius r as shown. So again, think about these L's, m, v's, and r's. You can replace them with any number you want, right? So it says, because the string sweeps out the surface of a cone, that's what it's doing, right? The system is known as a conical pendulum. So going back to what we said before, right? So conceptualize, we want to imagine the motion of the ball. This is what's happening. We want to categorize this as the ball is a particle in equilibrium across the y-axis, the vertical direction, but it's not in equilibrium across the x-axis, the horizontal direction. The particle is in uniform circular motion because it is tied to the ceiling, right? It's got one end is secured, and then you have some kind of energy that's been forced upon it. Now, this is assuming that there's nothing that's going to slow the ball down. It's going to keep having the same energy the whole time. Somehow this particle, it's got energy that's not going to stop. Nothing's slowing this ball down. Even though we've got gravity, right? We've got no force of air. There's no air friction or anything else that's going to pull the ball down in this particular case. It's going to keep going forever, right? All right. So here's the equations. So again, the reason why I'm giving the equations, guys, is if you need to solve a question on your test or think about this situation, right? You've got the first part, which is we're going to apply the particle in equilibrium model in the vertical direction, where, like we said before, the sum of all forces across the y-axis is the tension of the cable cos theta minus mass times gravity is equal to 0. This thing here, where we can say that T cos theta equals the mass of gravity. So that's the first equation, right? And then the second one is the sum of all forces across the x-axis is T sine theta, which is equal to mass times centripetal acceleration. Centripetal acceleration can be described as v squared over r, right? And so we take mass times v squared over r is equal to T sine theta, right? And we can get from that tan theta, if you think about this, right, is v squared over rg. Divide equation 2 by equation 1, right? So if we divide equation 2 by equation 1, so here's equation 2, here's equation 1, right? Then we get this equation, tan theta, because we got cos theta over sine theta, right? T over t, which is nothing. It's like t over something is always equal to 1. Cos over sine, so 2 over, it's actually sine over cos, right? Which is tan theta, right? And then you have the other part, which is mv squared over r over mg, and that's why you have this, where it kind of mass cancels out because mass over mass is 1. And then you have v squared over r over g. And if once you've done that, you get to this equation here. So tan theta is equal to v squared over rg. And then once you've got this, you can find out the velocity when you solve for v by moving things around. And you can say that v is equal to the square root of rg tan theta. And we get to that other equation that I showed you earlier on. Okay? Do you want to find the equation for velocity? So if the question, if you go back up to the top, if the question says find an expression for v in terms of velocity, in terms of the geometry that we see here, all right, that's what it does. If I want to find the velocity based on the numbers that I have, I can find that out. So let's do a practical example here. So if the radius is 5 meters, okay, it's a big radius, and the angle theta is 60 degrees, okay. Actually, let's just use 10 meters. It's big. It's a massive rope. It's a massive cone, okay, 10 meters, and the angle theta is 60 degrees, okay, as an example. So that's the length, and let's say the radius is 5 meters, right? What's the velocity? Do we care about mass in this particular case, right? Well, like we saw earlier, right? There is no mass in the final equation. If you want to find the velocity, mass cancels out in this particular case, right? We don't care about it. It's irrelevant. Velocity and mass, they're independent of each other, right? So if we say that the radius is 5, gravity is, let's say, 10, 9.8, all right? Let's just make it 10 for now so we can figure it very fast. So 5 times 10 is 50. And then what's tan of 60? Let's pull that up because you guys aren't going to help me today. I have a feeling. You guys are all tired, right? So we say, what's that? You picked it up already? You did it for me? Oh, my God. So 1.73 as approximately times, again, 50, right, is equal to this, approximately 86.6. I mean, I said 10 for gravity, but it's not really 10. And if I take the square root of that, you can see that it's 9.3 meters per second. That's what it would be if we use just this equation, okay? Notice also, what if we didn't have radius, but we had the length? We could also figure it out this way, right? So if we had radius, we can use this one. If we don't have radius, we can use the length of the cable, right? Yes?
Just the radius by using the length of the data.
Yes, we could. Yeah, we could do it. But I'm saying if you didn't have this, sometimes you're given different things, right? And in this case, we've been given everything, right? But let's suppose you don't have radius, you just have the length, right? And the angle, right? And then you can figure it out that way, where we calculate it. So we said 9.3 something, right? And if we did it the other way around, right, where we had, again, the length, we said it was 10 meters, right, times gravity. Let's say that's 10 meters. It's not really 10 meters. So that's 100 multiplied by sine theta. So we'll keep 100 in our mind. Sine theta, 60 degrees, right? So there's sine, 8.66, right, times 100, right? So we got this 86.6 times tan theta. Okay, so keep that in mind, 86.6 times tan theta, right? So tan theta, 60 times 86.6 approximately is equal to this, and then we take the square root of that, and we get something different, right, that we got here. And it could be because of the way I calculated it. But at the end of the day, you should get the same number because it's the same thing, right? LG, the length of the cable times gravity. And maybe it's different because the length, the radius and the length and the stuff that I'm giving you is wrong because I'm just taking these numbers out of my head, and they're not numbers that have been carefully calculated to give you the same answer, right? Okay, but that's the way it works here. For this example, that's not what am I doing? Okay, and here's the next one. A puck of mass, here we go, some numbers. 0.5 kilograms is attached to the end of a cord, right? 1.5 meters long, right? So this is the cord, 1.5 meters long. The puck moves in a horizontal circle as shown in figure 6.1, this thing here, right? If the cord can withstand a maximum tension of 50 newtons, so that's the force of tension, the maximum force of tension, what is the maximum speed at which the puck can move before the cord breaks? Assume the string remains horizontal during the motion. In other words, it doesn't do this, right? It doesn't flap, right? All right, so again, we can see the cord on upwards and downwards. The normal force is pushing the cord, the puck up as well as pulling it down. So there is no force of vertical motion. We don't care about that stuff. We can say that the particle is in uniform circular motion, but it's on the horizontal, right? Not making a cone shape. So the first one was a cone shape. This one is perfectly horizontal. That's the second example, right? All right, so we can say that the tension is equal to mass times acceleration, the centripetal acceleration, right? Or v squared over r, right? And given the information we had, we know that we have 1.5 meters for the length of the cord. That's the radius. That's the length of the cord. And 0.5 kilograms, right? So 0.5 kilograms. So here's the radius, right? And notice that we don't sub in the numbers before we get to the equation for max, the V max, if you will. And the reason for that is because we want to simplify this situation as much as possible, okay? Now, again, you could, this same equation, they've just put in T max and V max, but really what we're saying is the maximum cable tension can be, 50 newtons, right, as an example. So that's what we put up here. We say that the maximum cable tension can be 50 newtons before it breaks, right, times radius, and they've kind of rejigged this thing so we solve for V. That's all we've done here, right? So this equation here is just solving for V, right? And we can say that 50 newtons times the radius, which is 1.5 over 0.5 kilograms, and take the square root of that, is equal to the maximum velocity, which is 12.2 meters per second. Again, this is just subbing in the information we want and solving for V. But notice we started off with this equation. So tension is equal to mass times centripetal acceleration. All right, this equation here, okay? And the reason why I'm saying centripetal acceleration is we know that that's v squared over r, okay? Why am I saying that? Because you might get a question that says the centripetal acceleration is this much. The mass is this much. What's the maximum tension on the wire? Or if the maximum tension on the wire is 50 newtons, is it going too fast? One of those kind of things. And you can break it down. You can say that centripetal acceleration is v squared over r. All right. Here's the maximum speed of a car. All right. So again, a 1,500 kilogram car moving on a flat horizontal road negotiates a curve as shown in this figure, right? If the radius of the curve is 35 meters, so this is from here to the inside of the curve is 35 meters, and the coefficient of static friction between the tires and drive pavement is 0.523, right? Remember we talked about this? Tires on dry pavement, pretty good static friction, right? So it's 0.523 is not bad, right? Find the maximum speed the car can have and still make the turn successfully. Okay. So we got a 1,500 kilogram car. That's a pretty light car. Is it actually how much does do cars weigh these days anyway? Does anyone know?
6. About 1.6 tons, 1.7 depending.
7 metric tons? Is it right?
Yeah.
All right, cool. Is it a small car, average car? Do you know?
It's a mid-size sedan.
Mid-size sedan. Is that about right? So it looks like about right. And 35 meters is the radius. And we can see that we have a particle in uniform motion again, right? It didn't mention that the curve is banked, right? The curve is flat, which means it's not probably going, there's nothing to help the car go around the curve. It's going to go around the curve. We got to figure out how fast it can travel based on static friction alone, right? So again, when we look at it, we can say that the force maximum, right, is equal to the, again, the, let's zoom in here a little bit so you guys can see this stuff. I want you to be able to see it because, and it's going to be recorded so we can talk about it, right? Let's go back. So the force has its maximum value, force of static friction max, is equal to the coefficient of static friction times the normal force, right? Which, when you equate that, is equal to, when you make the relationship, is mass. So the force of static friction, sorry, the coefficient of static friction times the normal force is equal to mass times v squared max, the maximum velocity, over r, right? That is the equation that we want to find. So we can say that the sum of all forces across the y-axis, right, as an example, is 0 because the car is in equilibrium. It's not going to fly up or be buried into the ground somehow, okay? So we don't care about this one too much. But we know we have this one here, okay? Then we have v max, the velocity max, if you think about it, and it says that solve the equation of the maximum speed, substitute for n. So if I have the maximum speed and I have the force of, sorry, the coefficient of static friction times the normal force, right, as an example, which is the normal force going up and down, times the radius over mass, all right? And once you do a little bit of math, you can see that what they've done is they've taken the normal force and they broke it down into its components, mass times gravity, because normal force and mass times gravity is the same. They're in equilibrium, right? So we take away the normal force and make it mass times gravity. Once we have that, we can eliminate the mass, because mass times gravity over mass, right, as an example, gives us just gravity times radius. So we can say that this equation, the square root of the coefficient of static friction times gravity and then times radius, is the way we can find the maximum velocity, and then we just sub things in. Okay, that's what this is. And so we get something like 13.4 meters per second. That's the maximum velocity we can have before the static friction is countered and the car goes off into oblivion. So how did this work out? How do we figure this out? Well, we went back to this, right, where we said the force max, right? And you think about this, forces is mass times acceleration. There's mass and there's acceleration, v squared over r. Centripetal acceleration, right? That's what this is. Does that make sense? So we know this force max is equal to this, but it's also equal to this, which is it has to be equal to the coefficient of static friction times the normal force, right? And that's what's in balance, right? The coefficient of static friction and the normal force is in balance to keep the car from flying off into oblivion. And you have to think about how to get there. So please use this example when it comes to a car flying off, kind of into oblivion, right? On the maximum velocity before a car flies, if you will. All right, some numbers for this one. Now, this is very similar to the one we got on the assignment, by the by, right? Just saying. So a child of mass m rides on a Ferris wheel as shown, right? The child moves in a vertical circle of radius 10 meters, right? So this is the radius at the constant speed of 3 meters per second. So it's moving at 3 meters per second. That's pretty quick. Determine the force exerted by the seat on the child at the bottom of the circle and bottom of the ride, and express your answer in terms of weight of the child. Okay, so how many times does the child feel heavier, is what it's saying at the bottom of the circle, right? Compared to normal, okay? So the stuff exerted on him. So if you think about this, here's his velocity, and here's his normal force at the bottom, right? You can see that the normal force at the bottom is pulling away, and mass times gravity. It's kind of a much bigger tension than it is at the top, because of what we talked about earlier, which is the forces going in the same direction, right? In this case, we can say that using the formula that we're given above, that the sum of all forces, right, here is the normal force at the bottom minus mass times gravity, right, which is equal to mass times acceleration. Remember, again, force is equal to mass times acceleration, v squared over r, right? So we can say that this equation holds true, right? Once we move the the normal force on the other side, normal force at the bottom, right, as an example, and we solve for normal force at the bottom, we can see that mass times gravity plus, mass times v squared over r, we can remove the mass. We can say, or mg, in fact, we can say that mg is times 1 plus v squared over rg is the formula that we're using. I gave you that formula earlier. And when we sub in the information we've been given, for example, 3 meters per second is the velocity, right? 10 meters is the radius. Gravity is 9.8 meters per second. And then we come up with a number. And this number, 1 plus whatever it is 1 times mass times gravity, which is, so in terms of the child feels 1.09 or heavier at the bottom than he would at the top. Does that make sense? Because we're using a formula that says, hey, at the bottom you add, at the top you subtract, right? And in this particular case, we're adding 1 because we're at the bottom of the formula, the bottom of the thing. Now we're using the normal force because the normal force is going to feel different. The normal force is the amount of the total forces that the child is feeling at the bottom of the descent of the Ferris wheel. Okay. If we were going to do this differently, if I was going to find the normal force at the top, how would I do it? Do I do that part? I do. Here's determine the force exerted by the C on the child at the top of the ride. All right, let's see how this is. So now you can see that it's a minus instead of a plus, right? So mass of gravity minus the normal force at the top because they're in opposite directions, right? They're in opposite directions in this case, right? Is equal to mass times v squared over r. Once you rearrange the equation, you're going to get this equation here, which is mass times gravity times 1 minus v squared over rg. And then so you can see that the force at the top, when you sub in the values, seems lighter, 0.9. So 90% of the child's weight, if you will, because mass times gravity, if you think about that, that's weight, right? That's how much the child weighs. So the child would weigh or appear to weigh lighter at the top than he would at the bottom, okay? And if you look at the two, so 0.908, and this is 1.09, right? So he almost feels 10% heavier at the bottom, right? So almost 1.1. And he almost feels 10% lighter at the top, 10% lighter. Okay, just if that makes any sense. Now, I'm giving you guys these things because not just one. One thing is it's in the book, and the other thing is you got this question, which seems easy on the assignment, but I want you to think about what it's asking for you, from you for R2D2, right? So think about what it's asking, and we're going to go through that today in lab. By the way, any questions around this stuff before I continue? I'm just barreling through. No one's asking any questions. So, all right, keep your eye on the ball. So here we got a small sphere of mass m is attached to a cable, right, at the end of the cord of length r. So some kind of radius set in motion in a vertical circle about a fixed point O, right, as illustrated. So again, when it says this and it's a vertical circle, once you hear a vertical circle, that means it's vertical motion. Vertical motion is it's not uniform, right? Because of, so horizontal motion, that's uniform. Why? Because I have this ball going in, or a particle moving in a horizontal direction. The only thing that's pulling it down is gravity, but the gravity is being countermanded by the motion that I'm using, right? Whereas in this case, when I'm moving a ball this way, it's going to speed up and slow down because of gravity. It's going to speed up at the bottom and slow down at the top, which is going to give a non-uniform circular motion. Non-uniform circular motion has different formulas than uniform circular motion, okay? So different conditions. All right, so we know it's not uniform. That's the first thing, because we know it's vertical. And when we go back to it, we can see that we start getting a set of equations. So the sum of all forces, for the tension, force of tension, is equal to mass times gravity sine theta, right? And again, sine theta is the angle of the cord, right? As it's moving. If we want to find the angle, right? Because it says that Determine the tangential acceleration of the sphere and the tension in the chord at any instant when the speed of the sphere is v and the chord makes an angle theta. So again, what that's saying is I've moved this much angular motion, if you will, right, in a small amount of time, right, in this particular instant, right? So I'm moving that fast because the angle of motion is telling me how there's a relationship between that and the velocity. Okay, just saying. So once we have that information, notice that there is up here, do we have any velocity that's mentioned? Up here, right? And think about over here what we've been given. We've been given a circle, we've been given a radius, right? And it says when the speed of the sphere is v and the chord makes an angle theta, right? Sphere v, so sphere, velocity v, and angle theta, all right? So once we go down, we can say that the sum of all forces across in this tension, if you will, is equal to, we can, when we rearrange things, we can say that the acceleration is g sine theta, right? And then once we found this out, at is g sine theta, that's one part for tangential acceleration, or that's what that is, right? And what it's asking for is the tangential acceleration of the sphere. That's the first part. The tension of the chord is the other part. So tangential acceleration is mg sine theta, right? Which is equal to mass times acceleration. And notice that, again, the mass would just cancel out. If we're solving for acceleration, so tangential acceleration, right, again, forces, mass times acceleration, mg sine theta is this force of tension, right? And you can see that we just cancel out the mass in order for us to get the acceleration, a formula for tangential acceleration. Okay? And then when it comes to finding the tension, we can say that the sum of all forces, again, is equal to mv squared over r. I'm just going on this side because, again, we're looking at v squared over r is centripetal acceleration. Ma, mass times acceleration, that's Newton's second law. V squared over r is centripetal acceleration. That's the type of acceleration we're getting the tension for. Tension, we can relate tension with centripetal acceleration, right? The force of tension then would be something to do with mass times velocity over radius, right? That's what it is, right? Once we have that information, we can say that tension minus mg cos theta is equal to this. Mg cos theta is, we've got this formula from the tangential acceleration, right? Cos theta as opposed to sine theta. Sine theta for, let me just go back to the diagram so you can see it. So here we have this, right? And we're looking for tangential, so the tangential acceleration. Tangential acceleration means that it's on a tangent. It's tangent to the circle, right? That's what we're getting when we kind of traverse the circle. But here we're looking at tension. Tension is, this total tension is equal to mg cos theta, right? And the tangential acceleration is equal to mg sine theta, this line here. Those are the two components of the force mg, right? We're just breaking out these two forces, right? These two vectors, if you will. I've got two vectors. One that's going tangent to the circle. The other one that's going, you know, kind of toward the circle, right? If you will, or opposite of the circle. This one. And so you have this at any point along the circle. You have a different vector magnitude, right? This vector magnitude is going to be longer than the vector magnitude up here, right? Because of the way the motion is going. Is if I'm going up the circle this way, you can see that this red arrow is going this way, whereas this red arrow, right, which is this one right here, it's not red, but it should be red. This one is going down. It's going towards the same direction as gravity. So you can see that here you're going to have, for this particular case, you're going to have a different acceleration and a different tension compared to this one. So what does this mean, this theta angle? It means that from the bottom, right? So if I kind of swing my theta up here, it'd be a different angle, right? And then you'd have a different tension. Okay. Again, sometimes it's a little bit confusing to some. That's why I'm focusing on this stuff, because you may see these questions with different numbers on your test. I'm just letting you know ahead of time, right? So let's take a look at this. So tension is equal to mass times gravity, v squared over rg plus cos theta. Once we solve for tension, once we have this information, as long as we can just plug in the values that we've got. Now notice what we have here is velocity squared, over the radius times gravity. We know gravity. That's always something we have. Radius, we need this radius, and we need the angle and the velocity. That's a lot of stuff we need to know. Mass as well to find the tension. So lots of stuff to figure this out. And if we don't have all these things, then we have to, there's ways by using different formulas to replace some of this information, with the things that we do know. Okay. By the way, how the heck did we get mg on the outside and rg on the inside, right? Think about this. If I'm solving for tension, why would I want to put my, formula in terms of that? Well, think about this. If I got t here, so t, and I move mg cos theta around the other side, I'm adding to it, right? So it's mv squared over r plus mg cos theta. Well, I've got m. I can remove m. So I can say that, t is equal to m times v squared over r, right? V squared over r plus g cos theta, g cos theta, right? So how the heck did I get this down here? How did I get rg down here where I don't have a g down here at all? How did that happen, right? Well, if you do some manipulation, notice that we've removed m, that's okay, and mg cos theta, right, is, g cos theta is something that I have over here. So plus g cos theta. So how did I move that over here? I have to divide everything on this side by g. That's what I've done, right? I divide this by g and I divide this by g. And somehow it works out to be v squared over rg plus cos theta, right? So that's how it works out to be this. But that's, and if you notice, once we've done that, because we've taken g out, we've removed g, right? Remove g, we divide by every term by g is what we're saying. So if this original term was g cos theta and this one is v squared over r, and if I divide all terms by g to take the g out, g cos theta becomes cos theta and v squared over r becomes v squared over rg because we're taking the g out. Okay. So again, that's how we derive the formula. But these formulas here, these conditions, these cases that I've given you guys are the same cases that you're going to see on your test. Conical pendulum, horizontal accelerate, horizontal movement, vertical movement, some kind of Ferris wheel. Damn, it's even on your assignment, right? So those kind of cases are the things you can see with circular motion. Okay, that's really it. That's all I have for today. Again, there won't be a lab in terms of lab exercise this week. There's going to be, I want you to work on your assignment. So if you finished your assignment already, anyone finished their assignment? Assignment 2? No one, not even you? Oh, right. So please take your time in class this week in your lab to finish your assignment. That's what I want you to do. Start working on it with your partner at least, right? I'm giving you lab time for this, right? So that you don't have to do homework. I'm trying to minimize the amount of homework you have, guys, right? Because I know you've got other things happening at this point in time, right? You probably have other assignments that are going to start wrapping up, starting off with all your other courses. Please take the time this week to start your assignment number 2, maybe even finish it so you have free time and you can hand it in early. You have free time for what's happening over the next couple weeks. Where next week, remember, we're week 9 next week, right? And we're starting new stuff the week 10, right? So please work on the stuff that you have. Get it done earlier. That's why I gave you the extra week, right? What typically happens, though, I have to say this, is that no one works on it this week. Even if I give you lab time, you don't show up for whatever reason, right? And then next week, you're asking me a bunch of questions, right? Please don't do this, all right? This would be a very bad situation, right? It's just because I have to give you other things. They're coming up. There's other more important things that are burning that we have to do before the end of semester, okay? Any questions around today's stuff? Again, we had some practical examples, but there wasn't a practicum or examples that we did. Try and plug in some numbers for yourself in these examples that I've given you, right? So given this situation, these same conditions are the ones that I'm going to probably ask you in the test. Plug in some numbers, see if it makes sense, try these things out for yourself. I know there's no mark associated, but that way you can understand how things are moving. Guys, thank you so much. I'll see you in lab.